Hi everyone, I'm Martine and welcome to my e-poster about the development of a metrological flow cytometer for next generation biomarkers. First of all, what are the biomarkers we want to detect with our metrological flow cytometer? We want to detect extracellular vesicles, which are released by cells in the human body and can be found in all body fluids. Different cell types release different vesicles, enabling distinction between various states of health and disease, making extracellular vesicles a potential biomarker. A common technique to measure these extracellular vesicles is the high-throughput technique flow cytometry, where optical measurements of forward scattering, sideward scattering, and fluorescence determine the characteristics of particles in flow. The scattering of particles depends on their refractive index, and the refractive index of vesicles is around 1.46 for the membrane and 1.35 for their inside, relatively low compared to polystyrene 1.63 or silica 1.48 at 405 nanometer wavelength, which is commonly used in flow cytometry. And it also depends on their size. Most vesicles are below 200 nanometers and therefore hard to measure. A flow cytometer also measures the fluorescence, which depends on the amount of fluorophores and the type of fluorophore antibody conjugates bound to the surface of the vesicles. On average, vesicles show around 1000 MESF of fluorescence. To make sure measurements are comparable, it is important to keep an eye on the metrology, the science of measurements. The flow cytometer needs to be calibrated using well-characterized reference beads, such that the arbitrary units of scattering, in the figure shown on the y-axis, can be linked to SI units, such as meter, shown on the x-axis. Current reference materials, such as polystyrene beads and silica, don't give the same scattering intensities for a 200 nanometer particle as that extracellular vesicles do. It is completely different in their scattering intensity. Therefore, new reference materials, such as the hollow organosilica beads, are produced as part of the METVES2 project. However, there are no metrologically traceable methods where their characteristics, such as diameter, refractive index, fluorescence intensity, and number concentration, can be linked to our references, such as the meter, through a chain of calibrations in a liquid. And this is a problem to get comparable vesicle measurements. Therefore, it is the aim of my project to build, validate, and use a metrological flow cytometer to traceably determine the mean diameter of the particles, what is the smallest diameter we can measure, their size distribution, their number concentration, the refractive index, the fluorescence, and the Raman spectra. Because we also want to make chemically sure we are measuring vesicles or the chemical composition of reference particles, such that in the end the reference particles can be used in laboratories around the globe. So how would a metrological flow cytometer look like? And where is it different from clinical flow cytometers? Well, the first difference is that the laser which we use falls on a DMD, a digital mirror device. This digital mirror device consists of thousands of programmable little mirrors which can be used to program both phase and amplitude of the beam. Such we can shape the laser beam in any shape we want. In this case, we want the shape to be a donut shape. Using the pinhole as a spatial filter, we can select the preferred mode of the digital mirror device beam. The illumination shape facilitates decoupling of size and refractive index using meat theory. When the donut beam falls on the flow cell, light is scattered into all directions, including the first direction, the forward scatter direction, where we capture the Fourier signal and the live image of the flow cell, which is handy to see if particles are present in the cell. We also have an LED in the setup for measuring the wide field image in the flow cell. The second direction which the scattering can go is in this sideward scatter direction, where we also measure the Fourier signal, and the backscatter direction. The backscatter direction is normally not present in other flow cytometers, which makes it a unique feature for a metrological flow cytometer. And it gives extra information about scattering of particles. Also in our scatter arm, we go to the fluorescence and Raman signal. Using a broadband laser, the signal goes to the flow cell and can give fluorescence and Raman signal, which are captured through an athlon, which separates all of the wavelengths and images those on a CCD camera. Another unique aspect of our metrological flow cytometer are the fluidics. A syringe pump focuses the sample in a 50 micrometer channel, which is smaller than the channel used in clinical flow cytometers. And the flow with which the focus of the sample is established is in the nanometer per minute range, where normal flow cytometers are in the range of microliter per minute. This gives the particles extra time in the 100 femtoliter interrogation volume, collecting more information on the particles. Also, our round flow cell is unique for flow cytometers, so we don't need the refractive index coupling gel, which generates more background signal. The current status on our metrological flow cytometer is that the optics are nominally in place. We can already detect signal in the forward scattering, sideward scattering and backward scattering directions, with the Fourier signals on the top and right and the wide field image on the bottom left. However, the flow cell is now placed on a statue, as the mount for the cell is still on its way. We do have all the other components of the fluidics in place, so we think we can start real measurements as soon as the mount of the flow cell arrives. When we can traceably characterize the reference materials, calibrating every aspect of nanoparticle flow cytometry, the way is paved to use extracellular vesicles as a biomarker in the clinic.